to announce that Gabriela Sato-Polito will give us our seminar today. Gabi is a postdoctoral member at the Institute of Advanced Study in Princeton, and she works on various aspects of pulsar timing arrays for now, which she will tell us about in her talk. But Gabi got a PhD from Johns Hopkins University a couple of years ago, working with Mark Kamienkowski, and where she mostly concentrated on aspects of cosmology. But as I said, over the past couple of years, she's been thinking about how the evidence/protection for a stochastic gravitational wave background from PTAs has implications for the growth and evolution of supermassive black hole mergers. And so Gabi, take it away, and thanks so much for coming.
Yeah, thank you so much for the invitation. Yeah, I'll talk about what we're learning about supermassive black holes from these initial measurements by pulsar timing arrays. So I'll just start very not advanced thing. Oh, for some reason.
On your
side? Oh, it's like totally frozen.
Uh-oh.
Also, DT, you can minimize the zoom thing a little bit smaller.
Oh, yeah.
Okay.
That's right.
Okay, looks like we're back.
Okay.
Okay, sorry. Right, so pulsar timing arrays. The basic idea is to monitor pulsars across the galaxy. So pulsars are these spinning neutron stars that have this jet. As they rotate, every time they sweep your line of sight, you see a little blip as shown over here. And they rotate in a very stable manner such that you can construct very precise models for these objects and use these as very stable clocks spread across the galaxy. This is just a few examples that I find kind of nice, but these are some slightly older papers. This one over here is a paper from the Annual Frequency Control Symposium from '87. That's basically saying that millisecond pulsars rival best atomic clock stability. And this one on the right is a paper studying using X-ray emission from pulsars as a way to do navigation, like space navigation, so like a GPS when you don't have like global positioning. But basically comparing the stability of various pulsars with the stability of atomic clocks, and basically showing that these are comparable with each other. So these are indeed very stable clocks, and the idea then of pulsar timing arrays is to try to use deviations in the arrival times of the ticks of your clock to measure gravitational waves that are propagating between you and the pulsar. So the basic kind of order of magnitude twiddle math that you can do for how well you need to time these pulsars if you want to be able to measure what is like a plausible astrophysical signal is basically you're measuring your characteristic strain is this ratio of the deviation in your time of arrival to your total observing time. So you're measuring gravitational waves by changes in time over time. And if you want to target a particular strain sensitivity, reasonable number is like 10 to the minus 15, and your total observing time is something around the scale of 10 years. This means that you need to be able to tell that your pulse arrived 100 nanoseconds late, basically, after 10 years. So this is the kind of scale that you need to be able to time your pulsars to be able to measure gravitational waves. But this is now appears to be possible, which is pretty interesting. So to be a little bit more precise, we can define this quantity, the timing residual, as this relative change in the arrival time of pulses, or in the inferred pulsar period, sorry. So this is for example, a pulsar A in a direction p hat. The relative change in your inferred period will be proportional to the change in the metric perturbation on Earth minus the metric perturbation at the pulsar, and then projected along this Earth pulsar axis. So here, omega hat is the direction of propagation of the gravitational wave, and your shift in your arrival time of your pulses that you infer depends on this difference in the metric perturbation between you and the pulsar. So for the case of a monochromatic gravitational wave traveling in the z-hat direction. This is the familiar form of your metric perturbation. But pulsar timing arrays are expected to be in this stochastic regime. So here we're thinking about a single gravitational wave coming from a single direction omega hat. But you're presumably in this regime where you have gravitational waves coming from every direction in the sky. So you want to think about gravitational waves coming from all possible omega hat. And I can take the expression that I had before, and I can write this as an integral over the entire sky, over all propagation directions of gravitational waves. And I can also write this in terms of a Fourier expansion. So here f is the frequency of the gravitational wave that I'm expanding this by. The difference in my metric perturbation on Earth and at the pulsar are now this phase difference between the two. And I've grouped all of these geometric factors that I had mentioned before in terms of the direction of the pulsar and the direction of the gravitational waves into this FA, which is sometimes called the antenna beam patterns of gravitational waves. And I've expanded this in terms of my polarization tensors of gravitational waves. And the idea is then basically to now think of the metric perturbation, here A, which includes H plus and H cross, the two polarizations allowed in general relativity. It's to think of this quantity as a statistical field, not as a single binary in spiraling and producing this one plane wave, but that your sources, you have multiple of these coming from every direction, and you're thinking of this as a statistical field that has some value coming from each direction in space. So this is a superposition of plane waves. The mean of this field is 0. And the first non-trivial moment that you can consider is the variance of this field. And so if I consider the correlation between two different timing residuals, so here ZA and ZB are timing residuals from two different pulsars now coming from directions P hat A and P hat B, so two different pulsars A and B. The correlation between these timing residuals will be given by an angular correlation component over there, C, which only depends on this angular separation between your two pulsars. This angle is labeled theta AB over there. And the overall magnitude of this correlation will be given by this energy spectrum. So this angular correlation term is the so-called Hellings and Downs curve. It only depends on your geometric factors and on general relativity, basically. And it looks like this. So this is basically saying that when your two pulsars are roughly in the same direction, you have a maximal correlation for every, once you consider the gravitational waves coming from every direction in the sky, your two pulsars are either propagating with the gravitational wave or against the gravitational wave as you integrate over the entire sky. And these end up being maximally correlated. As you move these, as you're looking at pulsars that are more and more separated, at or close to 90 degrees, you become less correlated and anti-correlated. And as you go all the way to 180, now your two pulsars are either propagating with the gravitational wave or against it in opposite. They're always doing this in an opposite way. And these two things are not the same, and so you end up with this kind of lopsided shape of this correlation. So this is basically what the correlation between your pulsars is saying. But this is a general prediction that you get from general relativity, and basically that's why it's considered this kind of smoking gun signature for gravitational waves. And so it's basically what this quantity is telling you is that what you're observing are indeed gravitational waves, whereas this amplitude is telling you something about the properties of your sources. This is related to the energy density in gravitational waves, or equivalently the characteristic strain. But this is what these two aspects of your signal are sort of telling you about your sources. So this was detected for the first time during the summer of 2023. So this is just an example from the nanograph paper. This is the Ellingson-Downs correlation that was detected, and this is this amplitude, the energy spectrum that was detected. And this was reported across multiple pulsar timing array collaborations. So the European and Indian PTAs combined their data sets and analyzed these together. Nanograv in North America, Parks in Australia, and the Chinese PTA all sort of simultaneously announced evidence for the presence of gravitational waves. And please feel free to ask questions throughout the talk, by the way. But so this experimental landscape is this very global, enterprise with telescopes being part of these different collaborations around the world, including China, here in Canada, and without which this whole, all of the science that I'll talk about here would not be possible. But so for the rest of the talk, I'll basically discuss what are we learning from these observations. So I'll talk about how there's actually a pretty simple way to estimate what the overall amplitude of your stochastic background should be that allows us to interpret this based on other electromagnetic observations. And in particular, this is an upper limit to the estimate. And it appears that what has been detected is somewhat higher than what you would have predicted, which is a little bit curious. And then I'll talk a little bit about how an improved statistical modeling of your sources can actually allow you to capture some physical effects that can tell you more about the nature of the sources. And from this, we conclude that currently the signal measured by pulsar timing arrays already favor a larger number of your background being produced by a larger number of fainter sources over a few brighter ones, which is sort of a new conclusion. Okay. So coming back to our PTA, this panel here, over here is showing the characteristic strain as a function of frequency and the sensitivity curves for various gravitational wave detectors. And so LIGO, for example, sits here at higher frequencies. PTAs are sensitive to these nanohertz frequencies all the way over there to the left. And in general, the frequency band that you're sensitive to depends on the inverse of your observing time, which is on the scale of a couple decades. And the maximum frequency that you can access is related to the cadence with which you go back and try to remeasure the period of your pulsars. So this is what sets the frequency band that you can detect with PTAs. And the typical signal that fits into this band is illustrated over here. So this is just giving a sense of scale for the system that we'll be talking about. So, I mean, pulsars are in the galaxy. Typically, these are at a distance of a few kiloparsecs. Your sources are expected to be in spiraling supermassive black holes. These are at some large cosmological distances, say hundreds of megaparsecs to gigaparsecs. And the frequency that these emit in gravitational waves is twice the orbital frequency. And you can just plug this into Kepler's law. And so you can show, for example, that a 10 to the 9 solar mass black hole at these subparsec separations will be producing gravitational waves at around nanohertz frequencies. So this is kind of the typical system that we will be producing a signal in the PTA band. So your expected signal are supermassive, in spiraling supermassive black holes. What else do we know about supermassive black holes? There are a variety of observations that we've made so far that have been used for us to learn about these sources. So for supermassive black holes that live relatively nearby here means within the local, say, 100 megaparsec of volume of the galaxy. You can directly image these galaxies and study their properties. And in particular, there are known relations between, and well-studied relations between the properties of the host galaxies and the masses of the supermassive black holes that they host. And you can infer the mass of the black hole dynamically, for example, from stellar or gas kinematics, and you can infer their gravitational effects. You can infer their masses by their gravitational effects. And so here, for example, the x-axis is showing the velocity dispersion of the host galaxy, and the y-axis is the mass of the black hole, and you have these scaling relations between the two that are basically telling you, the probability of some black hole mass given some host property of your galaxy. And these are typically some power law. For supermassive black holes that are not so close, we're limited to seeing those that are accreting and shining as bright quasars. And the basic idea is that what quasars are telling you about supermassive black holes is basically through an energy conservation argument, also called the Sultan argument. But basically, you can think of, if you have some total amount of mass that is accreting and some fraction is being radiated away and producing the luminosity of quasars that we can directly observe. So this is showing the quasar luminosity function, the number of quasars per bolometric luminosity. Some fraction of this total material that is being accreted is producing this luminosity, and the other fraction is falling into your black hole and increasing its mass. This fraction is set by this parameter epsilon r. Then by observing the quasar luminosity function as a function of redshift and integrating over this, this is telling you what the total mass accumulated in black holes throughout the universe has been. So basically, the quasar luminosity function is telling you about the total mass accreted in black holes.
The epsilon r, can that be a function of redshift?
They can. It could be a function. I think here it's just written as a single parameter, but it could depend on. Then from gravitational waves, we're catching black holes that are in the process of merging, right? So the basic idea is that pretty much every galaxy that we look at has a black hole, a supermassive black hole in its center. Galaxies can merge, and therefore the central supermassive black holes may also merge. The exact way this happens is very uncertain. A lot of question marks here. But if this happens and they can shrink to these subparsec separations, that's where you expect to see them in the PTA band. So these are typically very early, and they're in-spiral, very Newtonian. They're not in this actual merging process where you see, for example, in the LIGO band, they're in this very early stage. And so you can think of the emission of every binary as basically monochromatic over here. They're basically emitting at a single frequency. Okay. So this is what we think we've detected with the current observations. And so basically, all of this comes into the energy spectrum, so the thing that sets the overall amplitude and the correlation between your pulsars. And this is basically the energy density in gravitational waves per log frequency. So how do we understand this quantity? Well, it's basically the integral over all merging binaries. So this is the number, for example, of merging binaries per redshift, mass, and volume times the energy per log frequency that they emit. The energy that they emit is expected to be entirely determined by just, so this is basically, you expect to be in this regime where gravitational wave emission dominates the evolution of your binary. So this is something that can be predicted just exactly. Just equate the change in the orbital energy by the power emitted in gravitational waves, and this completely sets the frequency spectrum of your gravitational waves. So this is the strain, it's just a cartoon version of this. This power law is set by this quantity, and you have this is why you have a very particular prediction for what the frequency dependence of the gravitational wave in PTAs should be, because it's just dominated by the evolution is just dominated by gravitational wave emission. So really the uncertain thing here is what the amplitude of this should be, which is set by the number of binaries that are merging. You can have some deviations from this, so I'll talk in the second half of my talk, I'll discuss this effect from the discreteness of your sources. You could also have deviations because of interactions with the environment, but the baseline prediction is that this should just be this very simple power law. Okay, so the question is, what should the overall amplitude of this thing be? And there are a few different approaches that have been taken in the literature. Maybe one sort of natural way that you might think about predicting this quantity is to maybe do some like scaffolding off of things that we already know. So for example, off of mergers of dark matter halos or of galaxies, and then you build supermassive black holes on top. You have to specify some kind of time delay. If you do it just in terms of the galaxies, you might have to specify like the pair fraction, the fraction of galaxies that host black holes in pairs. And I think you can see how this sort of accumulates a lot of errors once you try to do this, because you have to specify all of these things as a function of redshift. Time delays between the galaxies merging and the black holes merging are very unknown quantities. So I think this gives you a prediction for what the signal should be, but it also accumulates a lot of uncertainties. So another approach that you can take, which was pointed out by Amy in 2001, is to realize that we observe black holes in the centers of galaxies today, and we can use that to estimate the single black hole mass function. So just the mass function of black holes that are by themselves today at redshift 0. And we can think of all of these black holes as potential remnants of past mergers. So the black holes that exist today are possibly the remnants of mergers that happened in the past. And so if I suppose, for example, that every black hole in the universe that exists today has merged once in its history, then the number of single black holes today is just equal to the number of binaries per total mass at some redshift in the past. And I still need to specify what this redshift distribution is. But you can have this one-to-one connection between the black holes today that are single black holes to the binary mass function at some previous redshift. Okay? So if I do this, I can, yeah.
This assumes that the black holes are not kicked out of their halos when they merge.
Yeah, it's assuming that we observe all of the remnants, which if that happens, we would, yeah. But under this assumption, we can then rewrite the characteristic strain as a function of the single black hole mass function today, which is something that we can try more directly measure in local observations. So if I rewrite that expression like this, we have this dependence on the black hole mass function, and you still have some dependence on the assumed redshift distribution and mass ratio distribution. But you can also very easily take an upper limit by just saying that your mean redshift is 0, your mass ratio, the maximum value is 1/4, so you can just take an upper limit. And this gives you some upper limit on what the gravitational wave background should be. So I think that the cool thing about writing this expression like this is that you can really see what all of your astrophysical uncertainties can do. They can take you from like 0 up to some maximum upper limit set by these values that I mentioned.
Is there an upper limit? Because you're assuming merge once. Well, what if it merged twice?
This is the next slide.
So it's neither an upper limit nor a lower limit.
It is an upper limit. I'll mention what happens once you have multiple mergers in a couple of slides. Okay, and so from the right, so we can estimate the mass function today from local observations by just combining your scaling relations and a galaxy catalog where you can count basically the number of galaxies per property that you're using in your scaling relation. And this gives you a prediction for for your black hole mass function. Okay, so if I put all of this together, these are estimates of the black hole mass function for different mass proxies. So for example, different colors here correspond to different references in the literature that look at these scaling relations, and the different line shapes are different estimates that are either based on the velocity dispersion or the stellar mass. So these are just various estimates of the black hole mass function. And if I take these estimates and I plug those into the expression that I had before, we get these points over here at the bottom versus these points at the top are the values that were measured by current PTAs. And this difference is, I mean, a bit puzzling and is something I've been interested in. But yeah. Okay. So then the question of, could it be the merger history? So we assumed in the previous equation that all of your black holes have merged once in the history of the universe. So, you know, an obvious way to make more gravitational waves from the same remnant population is to just have them merge multiple times. And what you're doing by doing this is to just say, you know, let me add more layers over here instead of just one. And you can consider, for example, the simple limit in which everything merges with equal mass companions. And at each previous layer, you're basically saying that there were 2 to the n more black holes, because you're just splitting them in 2. But conversely, they were half as massive. And because your gravitational wave signal scales as mass to the 5/3, you get this factor of minus 5/3 at each layer. And you can take the limit as n goes to infinity. So you can add infinite numbers of mergers. And you can show that this converges to a pretty small number. So in terms of the characteristic strain, you can only get a boost of about 60% by having them merge, you know, an infinite number of times versus just merging once. So you can't really get a very significant boost by just having multiple mergers because you're always reducing the mass of the black holes at each previous layer. And if you add, this is for the limit of infinite and instantaneous mergers, but you know, if you have some kind of time delay, you're only diminishing the boost that you get even further. So
how much fuzziness in the result
sorry?
comes from, how much fuzziness in the result comes from the range of spin histories and relative orientations of the black holes when they do merge?
Is it, from the spin, you mean?
From the spin history and the relative orientations of the black holes when they merge.
Yeah. So we don't
assume that they always have aligned spins or they have randomly aligned spins, and how much difference does that make to that result?
Yeah, so that would basically, the main effect that you would get from that is that your final mass would not be just the sum of your 2 initial masses, right? You could have a change in, is that not what you're referring to?
Well, the final mass is never the sum between.
Yeah, by the amount that is carried out in gravitation. Right. So it would mostly serve to change that quantity.
Right.
By not a very significant amount. So the typical.
Well, I expect it's a number, not too much different, but.
Well, you typically carry away about 5%, and
5%?
5%.
No, you're saying the net energy carried away is 5%.
Yeah.
Okay. But no, I'm just wondering how much variation there could be in that number.
It's always a pretty small number. I mean, maybe you could get up to 10%, but it's not really going to make a difference to the amount that is found here. I mean, yeah.
Okay.
I mean, if you, it's going to make a small difference in the amount of energy that is being carried out. If you have this very large number of mergers, you can have a slight change to this, but it's not expected to be a very large amount. You go from like 5% to 10% or something, but it's not this like factor of like 4 to 10 in the characteristic strength square that I was mentioning. Okay. So then we ask about, what could we have done wrong in the estimate of the mass function? Like, could we have misestimated this? What would you need for you to make up this amplitude through a misestimate of the mass function? And so basically here, one interesting thing to keep in mind is that the gravitational wave signal, because it's weighed by mass to the 5/3, is always peaked at quite high masses. So this is the kernel, this is just mass to the 5/3 times the mass function. And you always have this peak that is, of course, above the peak of what contributes to the mass density. And so if you want, as a point of comparison, the mass density inferred from quasars to maybe stay the same, what you're really saying from the gravitational wave side is that you want to boost the high mass tail of your mass function, for example. So this would be a way to change this gravitational wave prediction while keeping the story more or less constant. And so we kind of explore a few parameters that are relevant for this high mass tail. For example, the turnover in your Schechter function, or the scatter in your scaling relation, so the scatter of this over here. And what we find is that if you want to produce this amplitude of the background, you need to live in the region of parameter space where these two lines cross. So if you want your characteristic strain and your gravitational wave density to match your predictions, you need to, and we pick these 2 points, x1 and x2, as a range of parameter space where these two quantities are satisfied. If you were to ask where, in terms of the velocity dispersion and the black hole mass, is your gravitational wave signal being produced? So these contours correspond to 50 and 90% regions of where your gravitational wave signal would be produced in these models. You can see that these do not agree very much with the black holes that we've observed so far. In other words, you'd be claiming that your gravitational wave signal is being produced by signals that live inside of these contours, which we've not really observed. So overall, the conclusion from this is that we need to be misestimating the abundance of black holes by a factor of 4 to 10, or the peak contribution over here, this peak value that contributes to the gravitational wave signal, by about a factor of 10. Okay, I'm going to switch gears a little bit. Are there any questions about this part?
I guess the main question is, that's a story about the average energy density and gravitational waves, but you are now picking up the more massive objects, and there are fewer of those. So how much does your orientation or position relative to the big massive things matter?
Yeah, that's a great question. It actually ties in really well with the rest of this talk. So if I haven't addressed your question by the end, please ask me. Yeah. Okay.
Yeah, I'm a little confused. So you say you're most sensitive to the most massive, which is small number statistics.
Yes.
For Chris said, do we know that the density of those ones are low enough? Are they just on the rays with exponential tail, so small fluctuation can matter?
Yeah, so you're never really in this so here, your peak is around a few times 10 to the 9. This is not a range where you're so suppressed where in your overall estimate, this is
saying it goes extreme.
Yeah, so they're like over here, right? They're not really, they're pretty well captured by your sample.
You say you can go up to 3 to 5 times 10.
Yeah, if you do this actually becomes a problem. So I'll get to this in the next part of the talk. So this is a conclusion that we arrived based on these arguments. Yeah. Okay, so can we learn more from the shape of the spectrum? So we've been talking so far about this mean amplitude of the gravitational wave background. But you expect that your sources are this discrete population. And assuming a discrete population basically leads to two main effects in your spectrum. One of them is this frequency to frequency fluctuation. So seen over here, you would see some fluctuation just by Poisson sampling of the number of sources that contribute to each of your frequency bins. And you would also see a drop off in the median, which is maybe a little bit less obvious to see, but hopefully will be clear by the end of the talk why this occurs. But so there are basically these two effects that are signatures of basically Poisson statistics in your overall spectrum that you can hope to model, and by comparing that to the data to learn something about this number of sources that is contributing to the background. So the basic idea, right, is, we do have access to this frequency information, the amplitude in a few frequency bins, and you can model this as the sum of the contribution to each frequency bin. So you expect each of these frequency bins to be described as a sum of the contribution of each individual source. And each source can be described as being drawn by some equivalent of a luminosity function for gravitational waves. So typically people, you typically model the number of sources per, say, total mass, redshift, mass ratio, but you can integrate over this and just think of the number of sources per characteristic strain amplitude. And this is the equivalent of a luminosity function for gravitational waves. This is shown over here for a few different frequencies and a few different models of peak mass. And again, your mean is just the integral over this quantity. The mean number of sources is the integral over this quantity. The mean, so this power law amplitude is the mean over h squared. And this quantity basically describes all of the properties of your gravitational wave spectrum. So one, I guess, interesting thing to keep in mind is, one, that the shape of this luminosity function, so these curves over here are showing the strain squared times the luminosity function, this basically follows the same shape as this kernel, this mass kernel that I was showing before. So just like it's peaked at some typical frequency, these will be peaked at some strain amplitude. So these basically follow a very similar shape. And a useful quantity to define is this characteristic number of sources, which is the total background, so the mean, again, the mean power law amplitude, divided by the peak here, so the peak of each of these. So in other words, if all of your background were produced by your most important strain, how many would you need? That's this characteristic number of sources. And this characteristic number of sources, you can write down analytically in a very simple way how it depends on your peak mass and on your frequency. And if you want to predict, why do these fluctuations start happening like here as opposed to here? What does this depend on? You might want to call, say, the characteristic number of sources equal to 1, the point where your Poisson fluctuations become important, and that's basically set by this field. So in other words, these effects are likely to be important at some frequency in your PTA band because this is a very strong function in frequency. So if your PTA captured, say, a decade in frequency, these will be varied by like 4 orders of magnitude, right? So the dynamical range in number of sources is very large in your PTA. So once you have this luminosity function of gravitational waves, you can predict the distribution of your total strain, right? So this is the quantity that we actually want to compare to the data. It's the probability distribution of observing a total strain amplitude squared ht, whereas before we were just looking at the mean of this of these distributions. But here we're predicting this total, the total strain distribution. And this can be described as the probability of observing, so again, this was a sum of NS sources, of a certain number of sources. And you want to describe how the total, what is the distribution of the total strain squared. And this is just given by the probability of there being NS sources given some mean value, which is just the Poisson distribution, times the probability that these NS sources will produce an aggregate emission HT squared. And then you want to sum that over every possible number of sources. And where this is just a convolution over the probability of each individual source. So you're just combining, you're just saying what is the probability of a sum of random variables. And this type of approach dates back to like 1950s radio astronomy. There's quite some literature on doing this, but this was, I guess, the first analytical calculation in this gravitational wave context. And these calculations, I guess, just pointing out that they become quite simple in Fourier space. You can do this convolution very easily by just going to Fourier space, exponentiating, and coming back, and you have your model ready to go. So for these different models that I had shown before, these are the corresponding distribution of characteristic strains that you would produce. The kind of state of the art was to Monte Carlo these distributions, which are these histograms shown here, but you can also predict them analytically in this pretty simple way. And the shape is quite intuitive. So the smaller your peak mass, the more you're dominated by these many fainter sources. And the narrower your distribution, the more Gaussian, so the more symmetric this looks. Whereas as you increase as you reduce your number of sources, and for example, increase your peak mass, this becomes more and more skewed, this distribution. There's a further simplification that actually makes this very easy to fit to data, which is that if you basically rescale your parameter, your characteristic strain, by this peak, this kind of absorbs most of your parameter dependence. So I can now write this luminosity function as this characteristic number of sources times this function mu. And this function mu is approximately universal. So this is an example varying a bunch of different parameters related to the distribution of your sources. These are different turnovers in your Schechter functions, different redshift distributions, and different mass ratios. And in terms of these rescaled variables, they look very, very similar. So this kind of defines a set of effective parameters that basically describes your data very well. So basically, if I specify two numbers here, the characteristic number of sources and say the mean, I can, with these two parameters, describe my entire distribution, the whole gravitational wave distribution. And so instead of varying all of these different astrophysical parameters, I just need to vary two. And here is the distribution of total strains as in these rescaled variables. So here, the shape you can see just depends on what the characteristic number of sources is. And this is why you had this drop off in the median that I had shown before, because the mean here that it's rescaled such that the mean is fixed to this dashed value. But the typical value that you sample, for example, the median, is shifting to lower and lower values as you reduce the number of sources, and as you go to higher frequencies, the number of sources drops. So this is why you had that drop off in the median that I had shown before. And so, okay, this gives us kind of a self-consistent model that only depends on two parameters and describes all of these features in the spectrum that can teach us about this number of sources. And so this is just a very simple scheme of how you can in practice do this with your data. So you can just choose this set of parameters, compute your characteristic strain. These, of course, depend on frequency, but they depend deterministically on frequency. And you can just compare that to the data, constrain your parameters, and then you can always go back to your set of physical parameters in terms of mass, redshift, so forth. So you don't really lose anything. And this is just an example of what was done in the main nanograv analysis, which does become a lot more complicated as you're building libraries of the binary evolution. You build various libraries from these simulations and Monte Carlo the distributions, but because that becomes very costly, you then need some like Gaussian processes to interpolate between your different models. And then you're still left with a bunch of these astrophysical parameters that you need to fit to your data. So this, I think, simplifies this process a lot and is what allows us to get to a kind of clearer interpretation of these observations. So, okay, this is showing, again, back into this set of the physical parameters of peak mass and the gravitational wave mass density. The blue contour is what you need to fit the nanograv data, and the red contour is what you would predict from your mass function today, from these scaling relations, and so forth. So the difference between these two contours is, again, this the same thing that I was describing in the first half of the talk. The dashed line here, these dashed lines, correspond to lines of constant characteristic strain amplitude. So if I had no information about the number of sources, about these Poisson fluctuations, the frequency to frequency variation, the drop off in the median, this contour would be completely degenerate along this dashed line. And so you can see that it is pushed a little bit in that direction because you do have some information about the number of sources, but you can't distinguish it from a simple power law. This is basically what this contour is saying. And then these dashed lines here, or the dotted lines, sorry, are lines of constant number of sources. And so this is, you're moving the degeneracy, you're moving in this direction because you do have some information about these numbers of sources. And you can see here that this scenario that I had described earlier of being dominated by a few times 10 to the 10 peak mass is kind of excluded because you would have predicted some of these effects to be present in these like lower frequencies of the PTA band where they are pretty well measured. So the exclusion here basically comes from the fact that you don't see a drop off in the median in your PTA, like in the low frequencies of your PTA band. Yeah, sorry, you were.
Oh, sorry. No, I just realizing what number of sources meant. So 0.3 means your average number of sources contributing in a given frequency is less than 1.
Yeah, yeah. And this is, I picked here just some frequency to plot this, but of course it still scales a lot with frequency, right? Yeah.
Is there any point where some assumption about isotropy of the signal breaks down in the analysis where you may not trust this, or is this?
So in principle, you can always just average over the entire sky. Like even if you just have one bright source, you can always just compute this, the total, but averaged over the entire sky. The point where this becomes a little bit trickier is that you're no longer, like the distribution in your likelihood is no longer strictly Gaussian. So that approximation can be kind of tricky. Yeah. Because you're assuming that your background amplitude is the variance of a Gaussian, and it might break this assumption a little bit, yeah. I guess conversely, you know that this isn't super important because you would have, people also search for individual sources, right? So if this is true, the point source, once you remove it, it would be a better Gaussian fit than if it were there. And the fact that you don't detect an individual source means that this assumption can't be too bad either. So, yeah. Okay. So basically, once we take this full distribution into account, we find that basically because you can't distinguish your gravitational wave background from a perfect power law, from something with fluctuations and a bunch of these features that I described, we find this preference for models with a large number of intersources over a small number of very bright ones. And so there's already some information in the background about the typical number of sources that we were able to kind of exploit from this model improved in modeling.
Does this increase the tension with the electromagnetic observations?
It basically stays the same. It just points to the fact that this solution that we thought was more reasonable because, maybe we mismeasured the tail of the distribution from these rare sources, just means that that's not super viable. But in terms of an overall amplitude, it's kind of the same. Okay, so, since we put out these papers, one thing I've been kind of happy about is that there's some discussion in the community. So there are a few options for different systematic issues that could be at play, both in terms of estimating the black hole mass function and in terms of the measurement of the gravitational wave background itself. I can comment a bit more on this after I'm done. If people would like to hear more about some of these options. I also co-organized a workshop where we talked about these things, and that was very helpful. And so I'll just leave you with my conclusions. PTAs opened this new observational window into the universe of nanohertz gravitational waves. There's a simple and robust way to interpret what this amplitude should be. And comparing this prediction with existing observations, you find some mismatch, which could be a hint of something interesting. The full gravitational wave spectrum can already tell us more about supermassive black holes, in particular regarding the number of sources that are typically contributing. And I think this kind of self-consistent modeling between electromagnetic observations and the gravitational wave signatures in all its glory will teach us more about these sources. Thanks.
Is there any role that eccentricity or environmental effects would play in your later, like the analysis of these?
Yeah, typically what these do is to these tend to, so the fact that your binary is losing energy by not gravitational waves just flat reduces this. So typically you get a suppression. It's an interesting signature that people are interested in searching for because that would be telling you something about the environment. It's an interesting signature. I don't know that it has a lot.
It's pretty independent of what you're.
I guess in some sense you do need your binaries to shrink to the PTA band. So there's some, you do need to have some environmental effects at some point if you want your binary to solve the final parsec problem and so forth. But there's not like a strong self-consistency prediction in the literature at the moment where, because if you're saying that every single binary needs to merge once, then you at some point need to make this efficient enough. So there is there's some requirement. It's not clear at the moment what it is, but
since your analysis kind of bottom up, right?
Yeah.
You've seen the merged ones.
Yeah.
Already.
Yeah. So our prediction doesn't depend on this, but I think it's an interesting signature nevertheless.
So what's the current thinking about accretional growth with this studies? What's your insight on how much Becker grows by gas accretion?
So I guess in general or related to this work. So in this work, we kind of ignore, in this work, we kind of ignore what this growth looks like. They operate in kind of different regimes in terms of redshift. So because these are the most massive black holes that are expected to live in the most massive galaxies, they're also expected to merge pretty late in the universe, so like below redshift 1, versus your accretion, like your quasar luminosity function, peaks at redshift roughly 2. So I think a sensible model is one where your black holes, these very massive black holes that dominate the PTA band, are just merging in the relatively late universe versus they grew from accretion presumably later in the universe.
And that's
Earlier in the universe, yeah.
That's still consistent with the quasar luminosity function.
It is. So there's one thing that's actually related to the paper I'll talk about tomorrow, but in this scenario where you have, in this picture, right, where your black holes merge in the late universe, but they accrete at redshift 2, where the quasar luminosity function is observed to peak. If you have multiple mergers, if say your black holes merged many times, what you're basically saying is that all of them had a lower mass in the past, right? If you merged a lot in the late universe, by redshift 2, you would have had much more abundant lower mass black holes, but you still have the same quasar luminosity function that you currently observe, right? So each of these black holes need to host the same luminosity of the quasars, but they're now much less massive. So one consequence of this multiple merger scenario is also that you really boost the Eddington ratio that you require. That makes sense.
You want it to be super.
Yeah.
I think a few people have been sort of working on trying to make gravitational wave maps. I think that there was recently some paper from the Meerkat data set where they were trying to, they had some gravitational wave maps for localized sources in the sky. And I think that there was one source one patch of the sky that was a bit bright, but not statistically significant just yet. So in that case, that if there were to be a bright patch in the sky, would you say that it would be sort of still like one bright source dominated versus like many dim, many sources?
I mean, this depends a lot on like what frequency this shows up in, right? If you have, again, the probability that that one source is much brighter than all of the rest is a very strong function frequency, right? So presumably, I think it's reasonable to assume that in some frequency bands of the PTA, you are more in this many fainter sources regime versus at some point you will cross this threshold and become dominated by a small number of brighter ones relative to the background. So it really depends on what frequency and where the elements are. Yeah.
So if I take it at face value, you're saying there seems to be 10 times as much mass in relatively massive black holes as we thought there was. So do you have any idea how strongly do you hold to that conclusion and where are they?
Good question. It's the title of the talk. Right now I've been thinking more in terms of, what are the possible systematics? Like what could we be getting wrong in terms of these estimates? And I think there are still possibilities that there are not properly modeled sources of noise in the PTA band, for example. I think this is an avenue that people are investigating a lot. So this paper, for example, is called Fewer Supermassive Black Hole Binaries in Pulsar Time Array Observations. It doesn't actually find that many fewer black hole binaries in pulsar time array observations, but there's a possibility, for example, that that the noise models that are fit to the pulsars are not super appropriate, and that would lead you to infer a higher gravitational wave background. But this has not been proven to produce an effect in this magnitude. But I've been told that there are other options that are currently being investigated in nanograph, for example. The other possibility is that we've not estimated the black hole mass function properly. And one thing I'm thinking about right now is trying to quantify these uncertainties better. So this paper, for example, is measuring a new stellar mass function that appears to agree with the background. But so I'm looking into this, and honestly, I don't think that there's that much room for variation in the mass function estimate. But those are the options I've considered so far. There's obviously, for example, the option that we're not actually seeing all of the remnants. So say some large fraction is kicked out. It is a bit strange that you would need, for every one black hole sitting at the center of the galaxy, at least like 5 others floating around that are like several times 10 to the 9 solar masses. Like, I don't know that that's like a natural prediction to make, but that's an option.
You're assuming circular binaries.
Yes.
How reasonable is
So there are models for the PTA. You can extend these models that I just described to include eccentricity, but in general, the effect is that you move a little bit of power from low frequencies to higher frequencies, and it makes a very small shift. So in general, you like suppress the power below some frequency, and you get a tiny boost above another one, just because, most of your emission is coming from if you imagine a very eccentric binary, right? Most of your emission is coming from when it's pretty close to when it's passing pretty close to the other one. But so it doesn't change the spectrum in a way that is super consistent with the data right now. For example, if you assume a very large eccentricity, you would predict a very large suppression of power at lower frequencies. And eventually it circularizes, right? So eventually you always recover the perfect power loss. So these are models that people are.
But there's also other physics coming in that's how like merger happens. So you have to keep that in mind.
There's always.
Talking about the eccentricity.
Yeah, I guess it just produces signatures that are currently not observed in the data, but they are models that people consider and try to fit to it.
Okay, we should stop there, and there should be snacks upstairs. And thanks, Gabi, once again. Thanks for joining online, people.